All right, good morning, everyone. Welcome to your first REACTO lecture. So Kate explained this yesterday, but the way this works is that we have a lecture every, well, usually Monday, it's Tuesday. Yesterday we introduced what REACTO was. So we have a lecture every Monday on some topic that tends to come up in technical whiteboarding interviews. And then that week we do a lot of problems that sort of involve that. Actually, every REACTO that we do and probably every technical interview question you have is going to touch on today's topic, which is, of course, big O. So I'm going to walk back from that particular jargon just slightly and ask, how can we measure the performance of an algorithm? Yeah, so how do we measure performance? And the answer is how fast can it do the thing? Great. What do we mean by how fast? Priya?
I was going to also add like space complexity is also.
Oh yeah, and like how much space does it take to do the thing? Which kind of like is begging the question because it's like, how do we measure fast? Like, what do we mean by fast, big, fast / space? Let's break that up. What do we mean by fast?
I think it's like how, this is so hard to put into words. It's like the complexity of your code, like how many things is it doing to do something to that one specific thing?
Yeah, so we could look at the code in some way and be like, how, like, tortuous does it look? Like, how does the code look? But this is, like, maybe not, and, like, eventually we will do something like this. We are going to analyze the code and be like, here's the structures, but just being like, how complex does this code look doesn't necessarily get us the answer, because, like, yeah.
It's the, if you have two for loops, then one process goes, and then another process goes for each of those processes. That's what I meant by the complexity of what it's doing to the thing, because that is what big O notation is, I think.
Right. So here's a, let's see. Here's a sort algorithm. How about like, or how many things does it do to the things? So here's a sort algorithm. This takes an array, and it's like while not array.sorted, not sort array, array.shuffle, and now return array. So it's kind of very simple in the code.
Yeah.
Who thinks this is a good sort algorithm? This is a really bad sort algorithm. It's also actually very hard to characterize in terms of complexity, but the answer is really a lot. So we are going to, you're right in that we are going to do something like this, but I actually want us to like really think about what we're trying to measure in our static code analysis. Yeah.
Mm-hmm. So what we're measuring is the number of, like how the number of steps grows as the number of inputs grows.
Yes, that is what we want to measure.
So how fast something can go is like how quickly can the computer compute that number of steps.
So I don't, yeah, so like how does the time taken scale to input size? Right, and this is kind of the core thing. I'm curious to hear more about the speed of electricity necessarily. I don't quite see the connection, but
Well, I mean, not that we concern ourselves with that, but like at the most basic level, like every single step is
And
at a certain, right, so like we have an idea of like how quickly, right, like a certain number of steps can, you know, it's like milliseconds, you know, to
right.
like 10,000 things or whatever, so it's like much quicker.
Yeah, so there is a fundamental limit to how fast computation can happen within space. We're actually not even remotely close to it in current processors. There's a limit imposed by quantum mechanics that says like there's only a certain amount of basically entropic reduction, which is what computation does, that can happen per unit volume of space. Probably it's not possible to make a computer that's that efficient, but we're still making processors that are more efficient every year, which is actually kind of the problem, because we could just say, okay, in order to sort an array of 10 million elements, this algorithm takes 30 milliseconds, and this other algorithm takes 10 milliseconds. But that's true like right now, and won't be true in about 1 minute when Intel releases the next processor, which is much faster. And so we want to find not the, what is the word I'm looking for? We want to use not the like absolute numbers, but the slope of the line, which is exactly what you said. We're asking, how does the time taken scale to input size, which gives us a, I'm not going to do the dimensional analysis up here. Basically, we're asking, like, what is the shape of the curve as if we plot the time taken by the algorithm as the size of the input grows. So, okay, what's the shape of the curve for time versus input size? It's input size versus time, isn't it? Which is exactly as loosey-goosey as it sounds. We really, there are formal mathematical methods to be like, oh, we're taking the limit as this quantity goes towards infinity. Nobody is actually doing that when we do complexity analysis. Like, that's probably not true. Like, some professors are doing that when they do complexity analysis. When most coders and really most working computer scientists do complexity analysis, we're kind of eyeballing the code, or maybe running a bunch of experiments, like just trying it with different input sizes, and then eyeballing the graph we get, and we're like, yeah, it looks like it scales like n squared, or 2 to the n. Which can be, and like the eyeballing the output methodology definitely has some flaws, right? Because you can never be sure that you've picked a big enough n to see the big picture scale. Like maybe between an input size of 0 and 500 trillion, it looks really a lot like n squared. Like the amount of time scales with the square of the size of the input. But then between 500 trillion and 89 quintillion, you can see that like, oh, it actually like starts to smooth out. And this was just a little bump in like a logarithmic complexity class. That's, first of all, kind of unlikely, and also kind of irrelevant if you were testing it with the data sizes that you're intending to use it at. On the other hand, we often, when we're like writing code and testing it, we're often using much smaller data sets than our code will eventually be used with, which is really why this kind of analysis is important. We want to understand that we're picking tools that are going to scale relatively well, or at least where we understand how they're going to scale as our programs have to chew through more and more data. Okay, so that's the general justification. We care about how will our code scale as our input size gets larger. And what are the basic shapes that we care about? In other words, like if I'm saying like the time complexity big O is basically describing the shape of the curve that maps input size to time, what are some shapes? So what are some big O's? Yeah, so there's linear. How do we express that? Yeah, it's O of n. And I kind of wish I had a I had this whole graphing thing set up, but when I launched it this morning, it didn't launch. So I'm just going to do ASCII art. So linear, oh no, that's constant. Linear should be something like all right, we're gonna, yeah, that looks good. So as n increases, the time increases. If increases proportionately. This is linear even though the line is kind of like sloping upwards at faster than, like this looks not quite like x equals y, y equals x, it looks more like y equals 2x or something. That's still linear because we care about the shape of this, but not the slope of it, not the particular slope of it. The reason being, we assume that the constant factor of the slope, so like whether this is 2n or 3n or 10n, is going to get dwarfed by increases in computational power. Okay, what are some other bigos? Yeah, logarithmic. I'm going to put that above n. Logarithmic, we call that O of log n. And, oh wow, can I draw a logarithm? Yeah, I'm not doing too bad. Kind of like that, right? That's almost good. Okay. So as n increases, the time increases as log n. This is not a very useful sentence, but what this tells us is that the time taken grows less at large n. So what are some? So that sounds great. What are some examples of algorithms that are logarithmic? Yeah. So binary tree search. Exactly. Also binary search on a sorted array. Merge sort. I think merge sort on the whole is n log n, which is a complexity class with a different name. I think linear log linear. But the merge part of merge sort is log n, I believe. No, that's the n part. What's the other part of merge sort? What's that? The sort part. No, there's like a
Yeah, the split.
the split. Yeah, is that sounds logarithmic? Yeah. Is it shuffle? Well, whatever. The not merge part of merge sort, because merge is O of n. I'm pretty sure. That just sounds right. Like we're plucking n things off of each array of size n. So these all have the quality that they're kind of these recursive algorithms where we divide and conquer. So we're taking, like in the case of the binary searches, we are at every step able to eliminate half of the data set because we choose a branch in the binary tree, or we're like, oh, I know this number was too low, and so I can eliminate everything in the array under it, which lets us scale very well with increasing data set sizes. Okay, what are some linear algorithms? What's that? Yeah, so like simple for loop that like touches each element in some way. Yeah, so finding an element in a linked list, finding. What else? Array, yeah. So search in an unsorted array must be linear. Some other good ones. The merge part of merge sort. There's a lot of linear time algorithms now that I'm thinking about it. Iterative Fibonacci. Okay. So this is actually kind of the big one. So the good reason for it to be first. Like, all of these are simple for loops that touch each element in some way. Okay, what are some other complexity classes? Polynomial, which is O of n squared. Yeah, really technically polynomial is O of n to the anything, and quadratic is O of n squared. Cubic? That seems somehow not right, but I'm going to call it that, is O of n cubed, and so on. What's that?
Cubic is also an argument.
Yeah. So this looks like that. Oh, this, I might have met my match with this one. Oh, it's not too bad. That's bad. Okay, well, that's kind of what it looks like. Okay, that's not bad. Whatever, it's ASCII. Okay, and then cubic I'm not even going to try for. But for these algorithms, the cost gets progressively worse as n grows. Whereas for logarithmic algorithms, the increase in cost got progressively better because because in an algorithm where you eliminate half the data set at every step, if the data set is bigger, you get more out of that fact by, as the data set grows. What are some polynomial time algorithms? Yeah, so nested loops, that's, basically for each thing in X, do something to each thing in X, each other thing in X. And that's the general template for every quadratic algorithm, basically. They're all going to end up doing something like this. Or, for each thing in X, do something to each thing in Y, where Y is about the same size as X. What are some examples here? How about array intersection? Or, so that's basically search in an unsorted array and then search in another unsorted array. Or for each element in an unsorted array, search for that element in a different array. Bubble sort. Not the best sorting algorithm for that reason, except in certain cases. What else? There's some optimization problems that we'll see later this week where the most optimal solution is polynomial time. Those are problems where your first pass solution kind of looks worse than polynomial time, but if you're clever about how you avoid duplicating work, then you can get it down to polynomial time. So I'm trying to characterize this NP, no, not NP problems, dynamic programming, optimized solutions. We'll talk about dynamic programming in a couple of weeks. I'm just going to leave that phrase in your brain, so you can read it on Wikipedia and be like, this is a really confusing practice, and then you can read about it and cracking the code interview and be like, I still don't totally get it. This was my experience with like dynamic programming, which is basically the act of breaking a problem into smaller problems. To some extent, it's intuitive. To another extent, it's like, why did you give it this name and like call it a particular practice rather than just problem solving? If you're feeling like, I just don't get how this is a thing, I'm pretty sure it's not. That's just how it is. It's just someone decided to give it a name. Okay, what are some other complexity classes that I'm not going to try? Yeah, what's that? Yeah.
It's like, do you do some dynamic programming sort of stuff with like some recursive things, like if you're calculating the Fibonacci number and like you're gonna have to calculate like n-1 or n-3 or something like 2 or 3 times, and you can just like hold on to it instead of redoing it each time?
Right, so that's a kind of optimization called memoization in the case of recursive Fibonacci, which is often used by dynamic programming solutions. It isn't itself dynamic programming, or maybe it is, like it falls under the banner of like optimizations used by it. Dynamic programming is sort of the practice of taking a problem with like many degrees of freedom. So like one example is, like, given certain rules about what boxes can stack on top of other boxes, what's the tallest tower you can build with a bunch of boxes? Which the naive solution means you have to try all of the different ways you could possibly stack something. But by being kind of clever about how you... Am I just gonna... Should I put on some techno?
There's still this lecture in there.
Okay. I kind of refuse to fight with a fire alarm for now.
Oh, by the way, according to Wikipedia, dynamic was chosen by Bellman to capture the time-varying aspect of the problems and because it sounded impressive.
This isn't just programming, this is dynamic programming, and I invented it. Where were we? Oh, right, so, yeah, boxes. So, I bring up boxes because there's actually a lot of, like, box optimization. Really?
Yeah.
It's like, they're about to come on and be like, please disregard these obviously disregardable noises. So those problems, basically it's your... Yeah, this isn't really a fire drill. No, 7. It's taxing.
I think it's I didn't actually read it.
Yeah. Anyway, if you're clever about how you build up the hypotheses, you can basically be like, oh, I can avoid like even considering all of these because I've already decided that this is less optimal than this other stuff in every possible way. So that process is dynamic programming, and then once you yeah. We weren't going anywhere, man. Yeah, so once you've broken down a problem in that way, if you can apply memoization and get this speed up. It's basically a way to structure a problem so that memoization can help you. Fibonacci is already kind of structured that way because you, like, the sub-problems are sort of very well spelled out. Okay. What are some other, like, complexity classes? Yeah.
Constant time?
Constant time. Oh, yeah, that one's great.
And easy to
So easy to ASCII. We call that O of 1, and it looks like this. Ooh. As n increases, time doesn't change. And what are some things that follow this? Yeah, so hash lookups.
You like look up.
What's that?
I was going to say just looking up like something in an object.
Yeah, so which is a hash lookup, or in an array, it's like a memory access, or array lookup. What are some other things?
If statements.
Yeah, so branches, if statements, like arithmetic
Variable.
on fixed size, on fixed bit width numbers. Variables?
Like it's defining a variable.
Yeah, so defining a variable actually takes 0 time if we're looking at the time taken by a line, because it doesn't have to execute at runtime, really. It's like a note to the compiler, or like the declaration is. The assignment is basically a memory move, or var x equals. Yeah, what else? I doubt concat is constant time because it's not, because it creates a new array. Well, there's length, which is just reading from memory. I can't think of anything offhand. Like, I can't think of any of the things that touch the elements. Yeah. This is why hash tables are so great. I love hash tables. I mean, there's access. There's array access. And, oh, actually, no. Push and pop are amortized constant time, meaning they will usually take constant time, but sometimes they will take much longer. So, like, push, pop, shift, unshift, amortized constant time. What's that?
Because like push and feel like
Yeah, you're right. Pop is probably always constant time. Push and shift. The unshift, I'm not even totally sure if it's amortized constant time. Or sorry, shift, I'm not even sure about. The way, what I mean by amortized constant time is, so the way JavaScript arrays are implemented is that there is a big chunk of memory that stores the array, and the memory is actually large enough, or it's like too big. What's the word I'm looking for? It's larger than is required to store all of the elements. So as the array grows, it's growing into this larger buffer. So when I'm pushing things onto the end of the array, JavaScript doesn't actually have to create a new copy and copy all of the elements into it and like allocate more memory. Basically, pushing onto an array and expanding it, it can be an O of 1 operation because it just has to write some memory and then change the length, the stored length of the array. But then eventually we get to the end of the buffer, and now we have a problem because when I call push, JavaScript does need to ask the operating system for more memory, which is a constant time operation. So ask for more malloc. And then it has to copy everything from the array into the new array, which is not a constant time operation. But if you're clever about what size you ask the new memory to be, then you can sort of claim this amortized constant time thing, in the sense that if when we run into the end of the array's buffer, we ask for a buffer that's twice as big. So we're going to copy all of the elements over into the new buffer, and we're going to keep pushing into that. And eventually we'll reach the end of that buffer, and we'll create a buffer that's twice as big and copy all the elements into that. What we can do is play this weird accounting trick where we say, okay, it took O of n time to copy the n things from our old array into our new one. We're going to slice up that time and attribute it to each push operation that we had to call in order to push items into the array to begin with. Which means that we divided an O of n operation into n slices and divided that amongst n things. So we put a constant time, so that's like a constant time operation divided amongst n things. So each operation was constant time in an amortized way. So it's like the credit default swap of, of computer programming. But it actually does work in the long run, right? Because occasionally, you might sometimes need to know that occasionally this operation will take longer, but actually you usually just care about the fact that when this operation is happening like millions and millions of times per second, it's mostly taking constant time. Okay. There's probably other constant time operations I'm not thinking of, but these are the big ones. Basically, like any simple JavaScript operation, and then math, and a few array methods. And then there's some other complexity classes that basically get steadily worse. What are these? Yeah, so exponential is O of 2 to the n. What else? I don't know the name for that. That sounds bad. Yeah, there's factorial, which is O of n factorial. What are some exponential time algorithms? There's a real famous one. It's about someone who died in a famous play. Sorry, okay, The Traveling Salesman. Oh. Sorry. Or generally like graph optimization problems, like find the best circuit. So like find the best circuit. Or route all these circuit traces, or it's another one, like find, box packing. So like, what's the best way to put all these boxes into a truck? So most of these problems, when you think about them, they kind of seem hard. Like, it kind of seems like they have a lot of degrees of freedom. Like, the traveling salesman problem is, like, how can I visit every city in the lowest, with the shortest travel time, where travel time is determined by the cost of the edges. And it kind of seems like if you do that naively, you have to try out every combination of cities, which is just a lot of cities. Oh, okay, that's...
I was just letting you know that there's a worse one.
Great. Yeah, that sounds... Okay, I believe that, because you have like n cities to choose from to start with, and then you've chosen one, so that's off the table, so then you have n minus 1. Okay, so it's worse.
There's also an exponential.
Okay, and that one is also deterministic, I think. So like, so there's a solution to the naivest solution to traveling salesman problem. Well, this is actually kind of, it might be hard because n factorial is every possible way of ordering n things. So if you have an n factorial solution, you are looking at just like every possible solution given these elements. What is it? And then you can evaluate it. Yeah, it's like the brute forciest of brute force for any kind of optimization problem. So like the brutest of the brute for optimization problems.
So should we do like n to the n where like you don't take out the current city that you're working on?
It's like, what if I just visit Berlin 20? No, I think if you don't take it out, then it's like it'll never end. Because because I can just. It's basically like one of your solutions is, what if I just move to Berlin forever and stay there? Yeah, so factorial, for anyone not familiar with this math, n factorial is n times n minus 1 times n minus 2 all the way down to 1. And that is like the number of ways of ordering n things, because you can pick one of n things for the first item, and then one of the n minus 1 things left for the second item, which means that you are going through every possible ordering of the array or every possible solution for an optimization problem where we're asking for like, what is the best way to order these things? That's probably not a tractable thing to do for even very small data sets, right? Like, consider capstone groups, as I have done frequently, spending many hours of my life. And while I've been doing that, I thought, gosh, I should be able to write a program to do this. But if I just wrote a program that was like, compute every possible capstone group and then score it, if we assume, it's actually not quite this bad because the ordering within a group doesn't matter. But if we just assume that it does for a second, that means that in a group of 30 people, there are 30 factorial combinations, which is 2 times 10, or 2 times 10 to the 32. My computer cannot evaluate that many possibilities within the lifespan of the universe, or several, in fact. Which is why we end up sitting there with note cards, moving them around, being like, no, but this person didn't want to work on a game. Okay. We look like Charlie, basically. Okay, so these are basically the answers we're going to get when we ask for the computational complexity of something. How do we figure it out? What are some ways of determining the big O? Yeah.
Like looking at every single line and being like, this line is this complexity and this line is this complexity.
Yeah, so let's look at an example. I've got an example right here. I'm going to paste it in. Oh man. Sorry, there's comments in my notes which have the big O's written on them, but I want to do this interactively, so okay. Yeah, so the answer is go through each line, figure out the big O, and then multiply the max of nested statements. We will do that now. Okay, so here is a function that shuffles an array. The big O of this function is, I don't know. Let's figure it out. So what is the big O of declaring some variables? We said it doesn't even really matter. What about assignment? Yeah, so this is O of 1, and then array.length is... Yeah, it's array.length is just a property, so it's O of 1 access. So this is O of 1. This while loop is, sorry? Yeah. So it's going to go from, oh yeah, I see. This is not the best shuffle algorithm. But yeah, it's going to go from array.length down to 0. Probably we should do that. It's called Fura Code. It's a font you can install, and then you turn on ligatures in your editor. Okay, so this is going to do whatever is inside the loop n times. So now we need to figure out the big O of what's inside the loop. So what is the big O of this assignment? And then the array lookup. Yeah, so this is O of 1. And then math.random, O of 1, multiplication, O of 1, and then floor, right? So, and the assignment is O of 1, so this line is O of 1. And again, this line looks basically like this line. It's an array lookup and an assignment, so that's O of 1. Array lookup, assignment to array. Assignment to an element of an array is O of 1, so it's actually interesting. I wonder if that is sometimes not true. In this case, it is true because I is definitely in the array, but if I said array of 500 million is that, I wonder if you might have to expand the array. It's a digression. This one is O of 1. And then this is another O of 1 assignment. Okay, so for loops, we say that the big O is the big O of like how many things it's touching, and then times the big O, the maximum big O found inside the loop, which in this case looks like O of 1. So O of n times O of 1 equals O of n. And then a return statement is basically free. So it looks like the worst big O inside this function is, yeah, O of n. So this is O of n. Okay, cool. Let's do another. That's. It does, sorry?
Is the return O 0?
There isn't really an O of 0. I said like declarations are, oh crap. I said declarations are O of 0 kind of because they don't even lead to generated assembly code. They're like notes to the JavaScript compiler saying, hey, this word, when you see it later, refers to storage that should be allocated in this function. But then by the time we actually get down to running the code, the var has basically been completely erased. Or the declaration itself has been erased. The assignment hasn't, so this assignment still has to happen. And this is maybe a subtlety that is like not really important. If you think of it as O of 1, that's fine too, because it's not going to change the complexity class of anything. Okay, let's do one more. Okay. All right. So let's do this. What is our big O here? What's happening on this line? Yeah, just the assignment. Yeah, and this is going to be O of n times some whatever is next. And then what's this? O of n. Yeah, so we can say it's O of n if we assume that n, that array A and array B are of the same scale approximately, and that scale is n. We might also, if they might be very different in size, we might decide that there are two variables. So we might say this is O of m, where n scales with a dot length, and where m scales with b dot length. Wow, I like the tilde as that operator. That's really nice. Okay. So this question mark can get filled in by the worst big O we see inside the loop. What are the big O's we see inside the loop? Yeah, so this is an O of 1 check inside an O of 1 branch, and then this is, yeah, amortized O of 1, we said. And so this is going to be O of 1, which means the worst big O inside of this loop is going to be O of m. So this, on the whole, is going to be, yeah, if we want, we could say O of n times O of m, which becomes just O of n times n. Because this like big O function, not really a mathematical function so much. Like it's kind of, you should imagine whenever you see it, someone being like, oh, it's like kind of the mathematical notation of hand waving. Yeah, so if we decide that that array A and array B are likely to be of very different sizes, we might annotate it this way. If they're likely to be of the same size, then we can just collapse it and say it's like, oh, it's O of n squared. But this might be very important because I might be computing the intersection of something that grows very fast with something that's like the list of categories on our website, which we think will be like 5. It just won't be large. All right. And then we talked a lot about time complexity and not as much about space complexity. Usually that's fitting because mostly interviews care more about time complexity than space complexity. In some rare cases, you'll get, maybe not that rare, but in like less frequently you'll get questions that are like, do this in place, meaning don't allocate any new memory, and mutate the data structures you were given. So space complexity. We usually care less because space is cheap and time is money, and also our lives. We usually choose to trade off, I think my Mac is about to go to sleep, to trade off space for time by caching and memoization, which is a form of caching. So, for example, you will say like, oh, in the Fibonacci sequence is not a great example, but like if you have recursive Fibonacci, the big O of that is actually pretty bad. It's 2 to the n, or like phi to the n. If you memoize it, then you trade off space for time. So you have a cache that grows as O to the n, as O of n, and because of that, your time goes to O of n as well. The reason Fibonacci is not a great example is that there's an O of n time O of 1 space solution. That is, iterative Fibonacci just scans through the numbers and doesn't take any additional space for each one. What else is there to be said about space complexity? Space complexity, I think, is a little bit easier to reason about, too, because it's going to be the largest, basically the size of the largest array. array or other DS you allocate.
So what's the space complexity of push?
So the space complexity of push is O of 1, because it doesn't take any space to run the push itself. The space complexity, for example, of quicksort done not in place, at least, like this naive quicksort, I don't know if I can, I'm not going to try and come up with it right this second, but a naive recursive quicksort where you're making copies of everything on the way down, the space complexity is going to be O of n, because you would have to allocate all of those copies.
So for push, is it again like amortized, like constant? It's like sometimes you would have to allocate the space.
I would say it's constant because I wouldn't account the space of the array to the space complexity of the algorithm, because the algorithm I would basically look at what additional space other than the data structure that the algorithm is mutating is needed. And that's something you could clarify with your interviewer, because they may care about like what is all the memory that's allocated by this, in which case, yeah, push might allocate more RAM. Okay. I think we have spent long enough on this. That concludes our discussion of Big O. You will never have to think about Big O again. No, actually, you'll be thinking about Big O not just this week, but for all subsequent weeks. There are some particularly interesting complex problems in the grab bag that happens near the end of senior phase. The last week of REACTO is like just a grab bag of random problems that you don't know what you're going to get. But this week, we're going to be particularly focused on Big O optimization, which means that most of the problems will have a